setup. So, okay. So now I should be able to go to pointer, pen, and yes, I can write. Okay. Okay, so as I was saying before we were so rudely interrupted multiple times, right? We had the example where we had equations of the form right, for the diagonal terms, and for the off-diagonal terms, we had equations of the form, right? And so we said we could write that in indicial notation by making use of the Kronecker delta. Right, where this first term on the right hand side, right, that only has value if I equals j, right? So that's only going to be expanded over the diagonal of the matrix. And so this bkk, right, this is the trace of matrix B. Okay, and then for the next example, I didn't do, but I asked you to invert this equation and solve for B in terms of A. Was anyone actually able to do that? You did. Okay. So did you? Was there a trick?
Yeah.
Because I know how I did it. I want to see how.
So can you see the?
Yeah. So you just. I mean, if you can describe it verbally, what you did.
I first solved means for B1 means BKK, the value of BKK.
Yeah.
I solved for that. What is the value of BKK in terms of A?
Yes.
So then I just
okay.
Put back into this.
Yeah. So it's basically the same thing, the same trick. This was just kind of one of those I wanted everyone to exercise their mathematical chops, right? So we have the equation Aij is alpha delta ij bkk plus beta bij. Right, and I think this is a little easier to think about in matrix notation. Right, so what does this look like in the direct matrix notation? Right, this is matrix A is alpha times the trace of B, right, times the identity matrix, right, plus beta B. Right. So if we rearrange this, right, we can write this as A minus alpha trace of beta identity, trace of B, over beta equals B, right? Now let's take the trace of both sides, right? So now we've got the trace of this right-hand side equals the trace of B, right? So trace is a linear operator, so I can distribute it through. So that gives me the trace of A minus the trace, well, again, since it's a linear operator, alpha can come out. The trace of the trace of B is a scalar, so that also can come out. So then we have the trace of I, all of this over beta is equal to the trace of B, right? So the trace of identity is just 3. Right? So that gives us the trace of A minus 3. Alpha trace of B over beta equals trace of B. Right, now we just rearrange, right, and solve for the trace of B. Right, so we end up with trace of A equals beta plus 3 alpha trace of B, or the trace of A over beta plus 3 alpha is the trace of B. Right, so now we can just plug this. This gives us how to write the trace of A with respect to B. We plug that back in, and then inverting it is trivial. Right, so everyone try and sort that out. It should be pretty straightforward. There's other ways you can do it, right? You could write out all the equations, right, so that you have a linear system of equations, and then do Gaussian elimination, just like you did in linear algebra, to invert the system. But I think this is kind of an easier way of thinking about it. And I threw it in there because I wanted everyone to play with manipulating matrix equations and manipulating indicial equations and being able to move pretty fluently back and forth between the two. Okay. So moving forward. Okay, so coordinate transformations, right? So in the notes, there's this example where I give the transformation matrix. So another thing is A, Q, and R are all common notations for transformation matrices, right? So depending on the book, depending on the assignment, depending on the exercise that I'm doing, I'll move kind of in between them without thinking much about it, but they all mean the same thing. It's just all a transformation matrix. It should be pretty clear by content. Right, so we've got this matrix. Okay. So I asked to complete this transformation matrix. So what properties does this have to have for this to be a proper transformation matrix? Right, by definition. Right, what?
Centrosymmetric.
A inverse is equal to A transpose.
Yeah, right? So it's right, that's by definition an orthogonal matrix, right? So by definition, A transpose has to equal identity, right? And A transpose A has to equal identity. What about the rows and columns of this, right?
The rows have to be orthogonal to each other.
The rows have to be orthogonal to each other, and the columns have to be orthogonal to each other, right? So that means the dot product. So if I use A1, A2, and A3 to mean the columns of the matrix, right? They're dot products. So AI dot AJ has to be 0, right? And the same thing with the rows, right? So in this case, the easiest thing to do, right, is how do I find a matrix that's orthogonal to the first row and the second row? Cross product, right? So the easiest way to finish this out and make it a proper transformation matrix is just the first row and a cross product with the second row, right? Or you can set up linear systems and solve. In the homework, I ask you to do it 2 ways, right? Right, but it's a very similar product, and instead of making it exact solutions, I I say do it to numerical accuracy, right? So I give you 4 decimal places, right? So you're going to want something that when you do A transpose A gives you identity to the 5th decimal place or something, right? So something that's easy to put into your calculator, right? You know, get used to you know, doing matrix operations on your calculator, or reacquaint yourself with MATLAB or Wolfram Alpha, or something that you can do these quickly about. Okay, so the other example, right? We have a coordinate system. Oh, that's a really bad. So we have x1, x2, x3. And then I say the new system is rotating by an angle theta about x3. Right. And I say what's the transformation matrix look like? Right. So this is one that in a couple weeks you'll just be able to rattle off the top of your head without thinking about. Because you'll be doing a lot of transformations by rotating about a single axis, because that's how we define crystallographic symmetries, right? Cubic, we say rotation about 1, 1, 1, right? Or rotation for other systems, tetragonal is rotation about 1, 1, 0. Hexagonal is about the x3, the cubic, the c direction of the crystal. Okay, so let's set up our direction cosines table, right? So we have 1, 0, 0, 1, 0, 0, 0, 1, right? And if we make x3 stays the same as 0, 0, 1, right? So x2, right? So what's the projection of the 1, 0, 0? So let's start with 1. Right, what's the coordinate of this point? Right, we want the projection on the x-axis.
X1 cosine.
Right, so that's just going to be from physics 1, right? You transform vectors into two components, right? So this just becomes cos theta 0, 0, right? What about this in terms of x2, right? This becomes sine theta, 0, sine theta, right? No, I'm screwing this up. I'm jumping ahead of myself, right? So this has to be cos theta sine theta, right? Now this here, the x component is backwards, so this becomes minus sine theta cos theta, right? And now when we do our dot product, this times this, we have cos theta sine theta 0 minus sine theta cos theta 0, 0, 0, 1. Right? And that's our transformation matrix. Right? But it's always the dot products, right? Is how we use to define this. Define this bit. Okay. Right, so the next one, right, I give you tensor B with components Bij. So just a notational thing here, right? Capital letters, capital bold, will always mean either the direct tensor or the matrix, right? Lowercase with indices always means the components of that tensor, right? So this is the ijth component. Other authors will do this. They'll take the matrix, they'll put it in brackets, and do that to indicate that it's the components. Notation in this field is screwy. Everyone has their own, and if you go into the mechanics literature and you read a paper, the first page is describing the notation, and then defining all the things we already know. Like, well, right? The first couple paragraphs of any solid mechanics paper repeats what's going to be in the next 2 lectures, right? So, yeah.
Earlier in an example, we encountered the trace of I, and we said it was 3. Should we, for now, at least assume 3 by 3 matrices?
Yeah, everything is always going to be right 3-dimensional, right? Yeah. Yeah, we live in a 3D world, so we're going to assume that indices always go to 3 unless otherwise specified. But yeah, that's a good question, because that's something I assume that everyone picked up on, but I didn't know if I actually ever specifically said it. So I've got this 2, 0, minus 1, 0, right? And then I say we're rotating 45 degrees about x3, right? So our coordinate transformation is square root of 2 by 2, square root of 2 by 2, 0, minus square root of 2 by 2, square root of 2 by 2, 0, 0, 0, 1. Okay, anyone not understand where I got that q from? Right? It's the same form. Cosine, sine, minus sine, cosine, right? And the cosine and the sine of 45 degrees is square root of 2 over 2, right? So what does my transformation look like for this? Right? So B prime is Q, B, Q transpose, right? So this is something that comes up at least once a year, right? How do I actually evaluate this product?
You do the first one first.
Right? Right. Remember, matrix multiplication is not commutative, right? So I can either do Q times B, right? I can break it up like this. Q times B, then times Q transpose. Or I can break it up Q, B, Q transpose, right? And then multiply it like this. But you always need to keep left and right multiplication distinct, right? I can't switch the order of that, because then if I did that, I would get Q, Q transpose, which is identity, right? And then I'd get B prime equals B, which obviously is not true, right? Because it's orthogonal matrix.
Right.
Okay, so I'm not going to work this through. Is everyone okay with matrix multiplication by hand? Right? I mean, I don't expect you to do it by hand, but like,
You should know.
You should know what's happening.
yeah, like you should work through. Maybe is it better if I trust that you can do this times this.
Yeah.
Right, my fingers always get confused. I point to the wrong places. But if you don't, just practice multiplying 2 3 by 3 matrices together. Multiply something by identity and make sure you actually get the same thing back, right? When you actually go through it, right? If you can do that, then you know you've got the procedure right. But again, I expect everyone to do this on their calculator, on their.
In general, we construct all the transformation matrices, right? Where we're going to be constructing them, or
Yeah, right. Unless it's something weird. And but for the most part, things are going to be crystallographically related,
Okay.
right?
So we'll.
Right? Or you'll be transforming something to the principal frame, right? Which means you'll be finding the coordinate transformation that puts your tensor along all the components are along the diagonal. We haven't talked about that's in the stress lecture,
Okay.
right? But you'll be transforming, say, a stress to the principal stress frame, doing some manipulations on that, and then transforming it back because it's easier to work with a diagonal than it is with a 9-component thing, especially things like finding the inverse or. Okay, so the last bit is this Neumann's principle, right? And this is something really important to keep in mind, right? We always need to be able to relate the symmetry of our underlying material with the symmetry of our properties, right? So how many people remembered off the top of their head that thermal conductivity for cubic crystals has to be isotropic? Right? So maybe a couple people, right? But it's all second order property. All properties of a material for second order that are described by second order tensors have to be isotropic for cubic, right? Because of the way the symmetry of the works out. For hexagonal, that's not the case, right? For tetragonal, that's not the case. For other, for others, it isn't. And it's really easy. So, as in the notes, I said, let's look at doing it for cubic. So we'll do it for cubic. And I'm going to leave the tetragonal for you guys to work out on your own, right? But so we have some second order tensor property, we'll call it K, right? So we have 9 components. We're not going to, it may or may not be symmetric, right? It may or may not. Okay, so what's the relevant symmetries for cubic? All right. What's the important one?
4-fold rotation.
Not 4-fold.
6-fold rotation.
Not
Cubic.
6.
There's 3-fold rotation.
Right. There's 3-fold rotation about how many axes?
4.
4 axes, right? Around the 1-1-1
Directions.
the 1-1-1 type directions, right? Okay. So let's write a transformation matrix for this, right? Okay, so there's our cube, right? We've got x1, x2, x3. Where's my 1-1-1 direction, right?
Along
It's the
X1.
body diagonal, right? So it goes from here to here, right? So that's my 1-1-1 direction that I'm rotating about. Now, if I rotate this, what does this do to my axes,
It moves X1 to X2.
right? So x1 goes to x2, x2 goes to x3, x3 goes to x1, right? So what does that do with our how does our transformation matrix look then? Right? x1 goes to x2, so 0, 0, 1 goes to 0, 1, 0. Right? x2 goes to x3, so 0, 0, 1. Right? And 1, 0, 0. Okay, So let's rotate about a different body diagonal now, right? So let's pick 1, 1, bar 1. All right? Okay, so here's my cube, right? So I'm going to, since it's 1, 1, bar 1, I'm going to make my axes up here now, right, for just to keep it
Easy.
easy, right? So my body diagonal now looks like this, right? And if I rotate about that,
X1 goes to X3.
right, what do I get? X1 goes to
X2.
minus X3,
Oh, yeah.
right?
I was rotating the other way for some reason.
Right? So I get 0, 0, minus 1, right? X2,
Goes to
right, goes to, right, X1 goes to minus X3. X1, X2 goes to X3. No, X3, sorry. X2 goes to X1, right? And X3 goes to minus X2. Right? So for cubic, the symmetry matrices are pretty easy to define. So let's start with our first one, right? And so I have K11, K12, K13, K21, K22, K23, K31, K32, K33. And then the transpose of this, rows become columns, right? So the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. Right? So that's my product. Right? So this one, let's actually multiply this one out, right? So I have 0, 0, K31, 0, 0, K32, 0, 0, K33, K11, K12, K13, and you see all of this is permuting the rows around in this one, right? So K21, K22, K23 times 0, 1, 0, 0, 0, 1. Erase. Did I erase the whole page? Right? And now, this gives me K33. Yeah, is that right? This, K33, K31, K32, K13, K11, and then the third, second times the third, K12. K23. You see why I don't do matrix?
multiplication.
Right? K21, K22. Okay, so now if I compare this, right? So now under this transformation, my crystal is the same, right? I can't tell that which one's the rotated, and which one is the original, right? So these values have to be the same. So I end up with a bunch of constraints already. K11 equals K33, right, equals K22, right? I now have K31 equals K12, K13 equals K32, right? So I have all these 6 off-diagonal terms that are also equal.
So doesn't that mean it's symmetric?
Well, not necessarily, right? Because my constraint here is K31 equals K12,
Oh, okay.
right? So it's not K21 equals K12, right? Otherwise it would be symmetric. Right, so we can go through the same exercise, right? And now we have K11, 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 right? Because we know those are all equal, right? I think I have K12, K13, K13. If I set all the other terms that are equal, right? 2, 3. What's 2, 3 equal to? 1, 3. I end up with 3, 1 is the same as K, 1, 2. And then 2, 2 is got to be 1, 3. Right? So I end up with this. So I only have 3 unique terms instead of 9, right, from the first symmetry operation. Right? Our second symmetry operation, right? Right, we have our matrix is now of the form 0, 0. Right. This is we're going to do around the 1, 1, bar 1 now. And what you'll see by when you multiply this out, you end up with the diagonal stays the same, right? But you'll end up with a lot of terms that say K12 equals minus K12, right? Which means those have to be zeros. So when you do the second multiplication, you'll see the K12 and the K13 term have to be 0, right? And that two symmetries is enough looking at 2 symmetries is enough to prove that it has to be isotropic. For tetragonal, right? What's the appropriate symmetry? Right, come on, you guys had structures. Most of you had structures with Trajan.
Yeah, there's a fourfold symmetry above the
About x3.
About x3.
Right? So what does that look like? Right? So
I mean, it's take a cube and
yeah, take a cube. I'm rotating by 90 degrees, right?
So our C is going to stay in, our x3 is going to stay unchanged.
Yeah,
but
so
our
we're going to
x2
have 0, 0, 1, 0, 0, right?
Yeah.
And then, so what's my cosine of 90? 0. Sine of 90
It's 1.
1. Right? And then I also have 180 degrees and 270 degrees that I also have to do. Right?
Yeah.
But the matrices all look
The same.
the same as this. It's just the
Negative signs.
the
change.
negative signs change. Right? And so if you'll do that, if you work it through, you'll see you'll have T1, T1, T3. Right? Is what you end up with. Right?
So what are we showing here? I'm sorry.
So this is if T is the second order tensor property for a tetragonal.
Arbitrary, right?
Arbitrary second order tensor property.
But you're just showing that through the orders of symmetry, only certain things survive.
Only certain things survive, right? So all set for if you're in a tetragonal system, so uranium,
Yeah.
right? You want to know what the anisotropy for the thermal conductivity of uranium is, right? It has to have this form, right? So anywhere in the AB plane, you're going to have a thermal conductivity given by T1, right? If you're along this C axis, it's going to be by T3, right? And it's going to be somewhere in between, regard where you are, depending on the angle between the two. But it's always going to be transversely isotropic, right? So anytime you rotate, right? So if I have let me draw it the same orientation. So here's my exaggerated, right, my tetragonal unit cell. If I'm looking along a direction like this, right, it's going to be between T1 and T3 somewhere. And if I rotate it about the C crystallographic axis, it's not going to change, right? So all the crystal directions that have that same angle theta, right, that property is going to be the same along them, right? So you get a whole cone of directions that have the same property, crystal directions that have the same property, right? And this is really really useful, right? Especially when you get into the weird things, right? So there's a lot of, we might talk at the end, you know, when we get to the kind of the open areas. I'll throw out a couple topics, and depending on what you guys think. One of the options is, you know, higher order and second order properties, right? So if you want to know what the Magneto thermoelastic tensor looks like, right? Right? If you want to know what these things are, you know, you can. This is really important for showing that it's impossible for a centrosymmetric crystal to be piezoelectric, right? Right? Piezoelectricity is third rank tensor, right? So you have to go through these operations, but then you can see pretty easily that all the terms go to zero, not just the off diagonal. So, okay, I think that's going to be it for today. So for next week, or for Monday, we are going to, I'll field a couple homework questions, and we'll go through some stress stuff. What exactly do we mean by the stress tensor, and different ways of defining the stress tensor. So the notes, the lecture for stress will be up tomorrow, and so please make sure you watch that part by Monday, and then make sure you watch the strain part by Wednesday, and the strain part will be up over the weekend.